Hi, and welcome to another Hopper on 6502 video. This one is about the minimal runtime and also a little bit about using Chat GPT to write code. I've got another video that's all on that subject, but let's get on with it. So what do I mean by the minimal runtime? So if we disassemble the current runtime that's sitting on this board over here, it's a Hopper virtual machine that's only 10K or 10,000 bytes of code to implement the Hopper virtual machine on this little 6502 board. It's an obvious focus on size over speed. So to try and make something small rather than worrying about how fast or slow it is. Anyhow, while I was waiting for this final version of the PCB to arrive to build the machine, I thought, okay, I'll try and experiment. Hopper has two 32-bit types that, even though the runtime itself, the virtual machine running on this board has 16-bit stack slots, which means you can have a 16-bit unsigned int, uint, or a 16-bit signed integer that'll run pretty efficiently in the Hopper runtime. But to be able to run a 32-bit type, like a float or a long, you have to sort of synthesize the behavior of that and treat them as reference types. So they're not very efficient in the Hopper runtime, and that's even if you're running on a PyPico. But on a PyPico, it performs a lot faster than this little machine, so you don't really notice it. So yeah, Hopper's never going to do, incredible floating point feats. It's designed to do what you do with an Arduino, like, blink LEDs and build little robots and things. It's not designed to do like, computer vision or machine learning or any of that stuff. Never was intended for that. Anyhow, let's get on with it. I decided to try and see what would happen if I added longs and floats to the minimal runtime. Now, as I said, it's still only 10K, so there's a lot of code to do, floating point division or floating point multiplication. And in my previous version of the 6502, I did everything in 6502 assembly. So I did this extreme exercise here of what would happen if I implemented long and float in Hopper rather than in assembly, knowing full well that it's going to be pretty darn slow. So let's have a look at what it looks like. So even addition. So when you're doing a 16-bit addition, a 32-bit addition, you're using the 16-bit types, and you're using it almost as if it was assembly. You're keeping track of the carry and passing it on to the next one. So addition's pretty straightforward to understand. Subtraction, pretty much the same. Multiplication is also pretty good because there's no loop involved. Division is where it starts to become pretty hideous because you're doing a bit-by-bit long division here. So 32 bits wide. And you're having to deal with the sign because it's a sign type. To write this code, I actually used Chat GPT to help me write not the long type. The long type's pretty straightforward, but for float I did. So to be able to write IEEE floating point methods for division and multiplication, even addition and subtraction are tricky. I used Chat GPT to help me figure out how to do this IEEE 4-byte float. But this is pretty hideous, and even things like toString, there's a lot of code that gets executed for toString. But let me show you how bad it is. So in the earlier version, for the 16-bit version, I added a seconds API for time rather than what we're used to from Arduino, which is the millis API, which is a long. Seconds is an int. And then I just did a little loop here, 0 to 10,000, and then timed it in seconds. So seconds is going to give us a very rough figure. It's going to be like, 1 or 0 or 2. And then at the same time, after printing that, I capture how long I time. This is included in the millis count here because it doesn't take very long. It's going to take the millis elapsed time, and it's going to do this subtraction, which is a long subtraction, and put it into the long. And then the thing that's going to take a really long time is the toString to output the long. with all this code. So if we right click on this, if we go to the definition of toString here, let's do that. So to do a long toString, yeah, it's not that hideous actually. It's pretty good. Yeah, it's not going to take that long. But then also timed out in seconds, because the seconds, we know the seconds timing isn't going to have much overhead because it's all in 16-bit types. But this will show us just how hideous it is when you try and generate floating point code in longhand, in Hopper, on a tiny little CPU like this one. Anyway, let's build it. So we build it in the IDE. This IDE is running on Windows. For those who aren't familiar, you can go and look elsewhere in the playlist to see how you can get this development environment running on your Windows machine, because it works with PyPicos or with, you know, my 6502 board, or with Ben Eater's one if you're running it on a breadboard. Okay, F5 to load the debugger. So you know, you switch the green title bar tells you you're in the debugger. And now I'll just Control F5 this to run it without. If you run it with F5, it's going to wonder if you press Control C or if you stopped on a breakpoint or whatever. So Control F5 should be full speed. So let's do that. So off we go. So the first thing we see in the console output is 1 second is what it took to do this first little section here. And then it lights up the LED to tell us it's in the second section. It's got out of that now. So the time for long, the actual time is, so it's actually 1.226 milliseconds. But the time it took to output that, to do the toString and all that, was 7 seconds, because it restarted the seconds timer here and set it there. So it took 7 seconds to do the output. So much longer than the actual benchmark. And since the light is still on, you know, the little LED, built-in LED is still on here, because it turned it on here again, and then turned it off here. It's busy calculating the time in floating point. So it did this floating point division. There we go, it's finished. And it zeroed the seconds time here to measure how long it takes to just output the time in floating point, for floating point. So it does a division by 1,000, and then it's going to do this toString. And this division and this toString took 45 seconds. So like, you know, way longer than the long, so 7 times as long as the long, and way longer than the actual benchmark took, which was only 1 second. Anyhow, interesting experiment. So, you know, I wrote a lot of code with Chat GPT here, you know, to try and get it to help me do, because I'm not an IEEE floating point expert, so to get it to help me to write these IEEE floating point algorithms for things like division and multiplication. It was quite fun to work this way with Chat GPT, but I fully expected this to be hideously slow. So why bother, you know? Well, it means that you can get proof of concept up and running on a different platform with very little code. So only having to have written, you know, the code for your native platform that's going to generate 10K of binary, assembly binary, and you've got full floating point, full IEEE 4-byte floating point support in a mere 10K of runtime. So yes, when they talk about trading off speed versus size, this is an extreme example. So you could get it up and running on a new platform, like get it up and running on a Z80, or get it up and running on a 6809, and you'd be able to time fractional time of a benchmark, because the actual API to go and get those 4 bytes of the fractional time is pretty quick. So if you don't care how long it takes for your benchmark to execute, you can actually do useful things with these floating point numbers. I also built and ran this on the Raspberry Pi Pico using the minimal runtime, and it's surprisingly fast. Because I've got a large test suite for testing floating point. So the large test suite, while it is obviously quite sluggish compared to if you're using native built-in APIs for floating point, it's still kind of reasonable on the Raspberry Pi Pico, not like this on the 6502, which is horribly unreasonable. Anyhow, safe to say that unless we port, I mean, you could port it now. So I mean, now it's great for prototyping and testing. So now that we have working floating point functions that work in Hopper running on the 6502. We could port these into 6502 assembly if we wanted to, but it would be quite big, so it would defeat the point of trying to keep that runtime small. And again, I could probably use Chat GPT to help me with the porting. It's very good at that sort of thing, like transformations from one language to another. It's not very good at trying to actually design something for you, but it's good at it would be pretty good at translating this into 6502 assembly if I ever wanted to. But I've got other things that need to be done first with the portable runtime long before I do that, like adding a little file system, because we've got this little serial EEPROM here which we use to store the current program, but it would be nice if it had all the file system APIs. So that would probably a much more practical thing to do in this way than trying to add floating point to, full 32-bit IEEE floating point running on a ancient little CPU is a little bit of a challenge. Anyhow, if you're curious as to how you generate this code with Chat GPT, I'll link to the other video on how I've been doing that and training it up on Hopper. And if you're curious about this board, I'll link to that video too at the end of this. Thank you for watching.